Okay, can you all see and hear me still after the recording has started?
Yep.
Excuse me. Great.
Yep. Yes.
Okay, so just a quick overview of who we are and what we do. We are Bruker Heisotron. So Heisotron started in the 90s. We're out of Minneapolis and then was bought by Bruker, I think in 2016 or 2017. I bring this up not because what I find important about that is that for you to know that Bruker left us mostly intact, which I think is pretty cool. What that means is that at the factory, um, I'm there, service is there, sales is there, production is there, meaning I can, if we're shipping an instrument to a customer before it ships, I can go back and log on and work on it if I need to. R&D is there and software is there. So that means that I can and I have, I'm having a problem. I can walk back to R&D and I can actually stick my head into the head of R&D's office for our division and say, I'm having this problem. Can you come help me? And I think that's a really powerful tool for you as a customer to know about, because that means when you reach out to us, my global tech support team, or if you reach out to me, we have a lot more, we're a lot more connected than I think many large companies are. So I just like to mention that we are, the 60-person company, even though we are Bruker, we're kind of all still based in the same in the same area and in the same building, which I think has great benefits for the customer. We are a nano indenter. We'll focus on quasi-static testing for the conversations today. Primarily what people are looking for is reduced modulus and hardness. As we go through and we talk about the instruments, we should be aware that the heart of the instrument is the transducer. What that means is that everything else around that system, the anti-vibration feet, the table, the granite, the XYZ stages, the piezo scanner even, all of that is built in such a way to get that probe into contact with the sample so that the transducer can do its job to the best of its ability. Let me, that work not here. There's often a question of where do we fall in material testing. On one end of the spectrum, you've got milli indenters, which require large force resolution and large displacement resolution, meaning that you're not going to get as fine detail as you would smaller ones, Vickers, nope. This requires you to be able to optically see the indent after you've done it so that you can measure it to make those calculations for hardness and modulus. One step up from that is micro, which has micronewton force resolution and nanometer displacement resolution. And what that means is that we don't have to optically resolve the indent in order to make those measurements. We are continuously monitoring both the force and displacement during that test. That allows us to measure that hardness and modulus. On the other end of the spectrum is AFMs, where you're running a sharp probe across a sample surface where you have sub-nanonewton forces, you have angstrom displacement, and you can get very high-resolution topographical imaging. Now, these are not indents. This is just a scan of the sample surface. There are some AFMs with tapping modes where you can interact with the sample and get some other information. What I like to point out is what ours does, this Heisotron scanning nano indenter. We're kind of in between. We're straddling this area of the mechanical testing world where we still have that nanonewton force resolution and we have angstrom displacement resolution, but we also have a combination of high resolution imaging. So our system can also image a sample surface to give us that information. Is there any questions about this slide? Whoa. I take it you guys are all together.
Yes.
Yes.
Okay. So how do we actually get hardness and modulus information out of the transducer? What I would like to point out is that the transducer is a 3-plate capacitive transducer, meaning you have a top plate, a bottom plate, and a center plate. And the center plate is connected to the sidewalls by these teeny tiny springs. It's really important for when we're talking about handling the transducer, because we have to make sure to keep those springs safe. If we bend those springs, the sensor is no longer functioning and there is no repair to be had. So it works because the outer 2 electrodes are fixed. To to measure displacement, we have an oscillating AC signal that's 180 degrees out of phase. As the plate moves through space, it allows it to work like an antenna, basically through an electric field. So as it moves, there is a relationship called our displacement scale factor between how far it moves and what that displacement actually means. So how that calculation is done. The force is applied to the center plate by applying a large DC offset to the bottom plate. This is bottom or top, but it is the bottom. It sets up an electrostatic attraction, and it causes that to move down then. We then have that also calibrated to a force, which is called your load scale factor. So each transducer is unique, and that comes with a calibration sheet that will have that information on it. So this is what it looks like at the end of the day. We get a loading curve as we load a tip into a sample, a hold, and an unloading curve. And so all of this information is coming from inside of that teeny tiny transducer. Which brings us to how do we actually do that calculation? So typically what people are looking for with the nano indenter, it, like I said, is hardness and reduced modulus. Our system specifically reports reduced modulus. Are you all familiar with Oliver and Farr? Have you heard those names? Is that on your radar at all?
I've been reading this in papers.
Okay, I would recommend reviewing the original paper. Oliver and Farr, I wish I could remember the year. I think it's 1993 and 1994. Kind of the founding paper of nano indentation. Short, it's a quick read, and it will help you understand the basics of this instrument a lot more. It also goes through all the math derivation, which I'm not going to do here for this training. We certainly can talk about it if we need to, but we will review it. So quasi-static testing, tip of well-known shape. Keep in mind that well-known shape, we're going to come back to that, is pushed into the surface while displacement is monitored continuously. Information about sample hardness and elastic modulus can be inferred. So we have this tip. Excuse me, sorry, there's one person waiting to admit. There we go. So we have this probe that is being pushed into the sample, and from the force and displacement information we get out of the transducer, we're able to then calculate hardness and modulus. So we have this loading and this unloading. We then do a power law fit to the unload. And when you take the first derivative and fit at the maximum, you get the stiffness of the material. From that stiffness, we get a lot of other information. So where that derivative intercepts the x-axis is what's known as our contact depth, which we will talk about quite at length. But what I want to note here is that the reduced modulus is dependent upon the stiffness, which we measure from the graph. Calculate from the graph would be the better way of putting that. You know, pi 2 and a square root of the contact area. Again, we're going to talk about that in depth. The hardness is dependent upon the maximum force, which we measure directly from the transducer. And again, the contact area. So here we can see that as we are indenting into a sample material, you're going to get both plastic and elastic deformation. What that means is that it's not perfect, right? You're not just punching a hole. There's some bending around that probe as it starts to indent. Sorry, I'm here alone, so I have to admit as people are coming in. So as that tip is pushed into that sample, is there a question?
No, Laura, don't worry about it. It's all our students. I can admit them.
Oh, do you have the way to do that?
Yes.
Okay, great. Thank you. So as that tip is pushed into that sample surface, you have some bending and deformation around the probe that's not actually in contact with the probe, which is what this is trying to show us here. So this is at the maximum force. We are indenting into the sample. You have this maximum depth, right? From the original 0 point of the sample surface, our max depth. Here's what our actual contact depth is. So you can see here that above this, the sample is not actually in contact with the probe. There is this contact area where all of the probe is in contact with the sample. Then, as it removes itself from the material, you get your final plastic deformation into the sample surface. So if we look at this graph, oops. If we look at this graph, That's what we're looking at here. Actually, this one has a better image of it. So here's our fit. You get our stiffness. You get your contact depth, where that stiffness fit intercepts the x-axis. This is your final displacement, meaning when the tip is coming out of contact, when the force goes to 0. And here's your maximum depth, so how far that probe got into the sample surface completely. Now, why does HC matter? So if we go back to this statement of tip of very well-known shape, it has to be well-known because the contact area is, the reduced modulus and hardness are dependent upon the contact area. So what that means is that if you have a perfect pyramid, right, which is what an indenter typically is, which we can also talk about all the different kinds of indenters and when you would use them, as you indent into the sample surface, if you take that pyramid and you cut it, right, where the contact depth is, if you're looking at it, it's going to be a triangle. And from there, you're going to be able to calculate the contact area. For an ideal Berkovich probe, so Berkovich is kind of the default tip for nanoindentation. The kind of rule of thumb is if you can use a Berkovich, you can. It's a very specific pyramid, three-sided pyramid with a very specific angle. If we went back to 8th grade geometry, I'm sure we could figure out how to do that calculation. You go down the pyramid and you cut it and you look at how far down you went versus what the area is, and you can make a relationship. For an ideal Berkovich, that contact area is 24.5 HC squared. However, we don't live in an ideal world. Of course not. It's nanoindentation. We're never going to be a perfect pyramid all the way down to the point. So there is some radius of curvature that occurs at any probe, with any probe. Excuse me. And our goal is that all of a sudden this idealized tip area function is no longer accurate, which means these results are no longer going to be accurate. So our hardness and reduced modulus results are only as good as our tip area function is. How can we fix that? So what we say instead is, wait, I have a sample that has a really well-known, well-defined reduced modulus of 69.6 that is constant as a function of depth. It doesn't have surface irregularities. It's well-known, well-defined, well-proven, and that's fused quartz. So what we do is we instead do an indent into the fused quartz and we switch this equation all around. We say, okay, well, the stiffness, I'm getting that from the graph, that information I have. I know what this reduced modulus should be, 69.6. So let's go ahead and let's solve for the contact area at this depth. And if you do it over and over and over again, you can start to define that tip area function. So this is all handled through the software, but we should understand where this is coming from. So our software goes up to 6 coefficients. We typically do 3 or 4. We tie C naught for a generalized tip area function. There are some exceptions here. I have two ends of the spectrum. I have a customer who is only doing thin films and he only indents like 20 to 30 nanometers. When you're doing that kind of indentation, the tip is never going to act like an ideal Berkovich probe. It's going to be blunted. And in that case, we let C naught vary. And we only do indents in the contact depth he is interested in. So we only do indents in the fused quartz at that very low value to get an accurate tip area function. On the other end of the spectrum, I have a customer who is testing cow eyeballs, which are very soft and squishy. She is typically going about 4 microns to 5 microns deep into that sample. At that point, the contact area is ideal. The Berkovich probe is going to be ideal at those deeper depths. If you think about the pyramid, right, the blunting only occurs here. If we cut it down here, it's going to act like that ideal Berkovich. She doesn't really need to worry about these other coefficients so much because of that. However, for most customers, we're trying to make an idealized tip area, or excuse me, a tip area function that can function well over a range. We want to make sure to not over-constrain it so that that C naught can lead that 24.5 at deeper depths. And then at shallower depths, we have the information that we need to have an accurate tip area function, even though it's not acting like an ideal Berkovich probe. Are there any questions there? I'm going to let you guys think about. Yeah.
Laura, you mentioned that for this researcher who are indenting for like 4 or 5 nanometer, and you said the Berkovich indentator is a fit, while the 20 nanometer indentation is.
I said 4 to 5 microns, not nanometers.
Okay. Okay.
So
okay, macro.
I remember that very specifically because I was debating whether or not to say 4 or 5 microns or 4,000 to 5,000 nanometers.
Okay. Thank you for clarifying that.
Yep. Okay. I'm going to let you guys think if there are any more questions while I grab a drink of water really quick, and I'm going to grab a different PowerPoint to share. So let me stop sharing here for a second. Okay. Let's try this again. I actually have a document that kind of breaks down specifically the TS-77, which is your instrument, correct? I have that note correct? It looks like this.
Yes.
Thank you. Okay, so I'm kind of gonna run through this too because you guys have received some base training before, and I just want to make sure that we're covering everything. My goal here is to make sure that if I touch on something that is unfamiliar to you that you need more explanation on, please let me know. I don't know where we all are in this training. I want to make sure that we cover as much as possible, so don't be afraid to interrupt. So a quick introduction to the TS-77 Hydrotron Select. Bruker Hydrotron itself, we make a lot of nanomechanical instruments. We make both platform systems, meaning ones that stand on their own, like yours, and then we also make models that go into TEMs and SEMs. Your system can do capable of doing standard indentation, dynamic testing, and increased force testing. I believe that you only have a singular transducer that is a 2D lateral transducer. Does that sound correct?
I think so.
Okay, I'm like 99% sure on that, but I didn't have the document pulled up in front of me. So you can ignore this, but basically you have standard indentation and you are also able to do what we call scratch testing. So this is this is the same thing, but a little bit more in depth about different mechanical testings. So we're going to go through, we're directly measuring force and displacement. And from that, we can make quantitative measurements using the appropriate models where we can get modulus hardness, creep, stress relaxation, fracture toughness, tan delta, etc. are possible on this instrument. I want to talk quick because I'm not on site with you. I do want to talk a little bit about the physical, the hardware, just to make sure that we're on the same page about what's what. You have this enclosure. A note about the enclosure is that I am just tall enough that I can sit and write. I always want to let it go because I'm just like half an inch. Don't do that. Make sure that you are controlling it all the way up so it doesn't jump on you. Be gentle with it. If you have to move it, don't lift it by the struts. Underneath that, we have a granite stage. The granite is on top of these little anti-vibration feet. And the granite that holds it is about, I think, 90 pounds. And that is to add some extra anti-vibration, some stiffness to the system. Below that, you have the electronics rack, which comes with a Bruker motor controller that drives your X, Y, and Z stages, and your NI control module. That's the brain of the instrument. It has your DAC cards, it talks to the software, it takes your data. That talks to your computer, which has the software called Triboscan 11. Here's kind of a better view of that standard transducer, where you have that outer electrode and the center electrodes with your indenter directly connected. And here's what it looks like. So I also bring this up because I want to be very clear that the standard transducer is just this U-shaped component. The part it's attached to is called your piezo scanner. And I want to be clear about that because in the discussion, when we talk about keeping things safe, I want you to know what information comes from what part of the instrument and also what parts to be extra careful with. Both the transducer and piezo are very fragile, but in very different ways. So nanomechanical testing, you can do depth control, position control, site specific. This is all just kind of examples about what's possible. You also, this is an indentation. Here's a scratch along a sample surface, nanoware. Oh, that's what a Berkovich probe looks like. It's a really wide pyramid. We covered most of this. We don't have dynamic testing, so we're going to skip over that.
One thing before we move further, Laura, I think Jim, the on-site installation engineer, he said like for the hardware of the machine, there is an order of turning on, like it's all from up down, right? It's a computer and there are two a controller and then the modifier or some a module, the control module.
Yeah,
And
the NI control module. What's important is that the computer is fully turned on before the controllers are. The order of the controllers, the monitor, that doesn't really matter, but the computer has to be fully on before the controllers can be turned on.
okay,
The reason
when
the reason is that they only look for the computer once. So they turn on, they look for the computer. If they don't see the computer, they don't try again. So that's why the controllers have to be done after the computer.
okay, for closing, is there any procedure or
Close the software first. Let it
okay?
completely close. Other than that, the order is not important. It's really when you turn it on, you'll get an error that says that the controllers aren't there, which isn't true. We both know that if we don't follow the correct startup procedure.
Okay, thank you.
Yeah, no, thank you. Good question. So implementation of testing. Oops, sorry, one slide too far. I like to answer this question before it can get asked is how long? You walk into an empty instrument and you have a sample in your hands. How long does it take you to get set up to make sure that you can test that sample successfully? And the answer is anywhere between 2 hours to 8 hours, depending on how well the system is set up to begin with. Now, for you guys, your system only has that one transducer. Many of my customers have more than one, so they're swapping transducers, swapping probes all the time, which can make the setup take longer, right? That's why instead of an SOP where it's like, do this, do this, do this, instead I ask it as a series of questions of, is this accurate? Is that accurate? Do you have a good tip area function? So that's what we're going to cover during training, is that there are 5 questions that we have to answer in order to make sure that we have set up the system well. So it can take up to a full day. You need to have your indentation axis calibration completed, your tip to optic calibration. You have to have all the samples defined, and you have to have an accurate tip area function. And then the question is, what makes a good sample for nano indentation testing and roughness? We want the roughness to be less than, we need to indent 10 times beyond the sample roughness in order to get accurate results. That means that you can test a rough sample, but you have to make sure that you're going deep enough to get beyond that roughness. It is nano indentation, so the less rough of a sample, the better. You need clean samples, and it needs to be rigidly mounted. This is something that I think is often missed in training, is how to mount a sample well. Your system has screw-in sample mounts available should we need them, but typically we find that the magnet is sufficient. So there are magnets in the stage, and our typical recommendation is to glue the sample to a AFM puck and test it that way. Now, people often want to skirt this, but you have to use super glue. People try to use things like whiteout or double-sided tape. They're too compliant and they're too drifty. You're not going to be able to get accurate results. So nano indentation, I think, can feel very divorced because you're sitting at a computer and you're running software, but we have to remember this is a very physical act. We are physically pushing a tip into the sample, and everything around that matters to make the results good. Are there any questions on the system itself or the Oliver and Farr tip area function information?
So far, we're good.
Okay.
Anybody
All
else? I'll take as a no.
Then I think we can go ahead and get started. So the first question that we need to ask is the hardware properly installed? So let me grab a picture of actually, was that a good enough picture? Yeah, that'll do. Let me go back to that PowerPoint for a moment. So for your system, You can see the feet here a little bit better. For your system, you have these XY stages, or axes 1 and 2. You have the sample stage, and you have your optics. Those should never move. There's no reason for a user to move those items around unless we're doing troubleshooting of some sort. What is removable, this is actually a bad picture because this is the original design, which had it bolted directly to the stage. This is your piezo scanner, this black rectangle with the tube coming down. And it slots into dovetails here that you come down. Your transducer then mounts to the end of that piezo scanner, and you then tighten that down. The piezo scanner is really delicate because so the scanner is what's in charge of moving the transducer over the sample surface during imaging, which means it is 5 different piezos. So there's a Z ring piezo that extends and retracts to move the tip up and down. And then there's XY quadrant piezos. Piezos don't really like being curved. It's hard on them. They're extremely fragile, and any lateral force to the end of that piezo dovetail can cause damage and can cause it to break. The most common way I see people doing that is by not defining all of their samples. The system is only as smart as you make it. If you don't define your samples, the system doesn't know that it's there, and it has no way of keeping itself safe. So we have to remember that the system is also doing a lot of stuff in the background to allow it to perform automated testing. Transducer is here. I don't expect that you'll be removing the piezo scanner very often, if at all. But you should know there is on the dovetail on the side of it is a 1/16 hex screw that you screw in to get it tightened down well. The transducer has a probe that you install using this probe tool that you can see laying down on the stage here. What I want to talk about here is how to install that. So I don't have it with me, and I believe that we were pretty comfortable with the hardware, so I'm just going to review this for the sake of the recording, actually. So there are a couple of key things to do when you install the probe. First, I always recommend you clean it. I don't care if it was cleaned before it was put away. I don't care if it hasn't been used. We're at nano indentation. We should always be cleaning as we go. It's much better to clean now than to get the entire system set up, realize you have a dirty probe, have to take it apart and do it again. The cleaning is documented both in the manual, and I'm going to make a shared resource folder with a bunch of documents. And there's also a document that will be there. But basically, you take a Q-tip and you fluff it out, and you hold the probe in your hand, and you can use either methanol or you can use acetone followed by isopropanol. The reason is that both methanol and acetone are strong enough to remove stickier contaminants. Acetone has to be followed by isopropanol because acetone leaves a residue. The isopropanol can then clean. So you soak your Q-tip in your solvent, and then you very, very gently rotate the probe and brush that fluffed end of the Q-tip against the probe. This prevents damage to the probe, prevents blunting, keeps it safe while also still cleaning it. You then insert the probe into the probe tool. It has a square cross section, and the probe is square up until the very end where it's round, so it will sit in there. Keep in mind it's only held in with gravity, so we don't want to dump it over. You should have your transducer sitting on your desk, and the number one rule is don't hold it. People are tempted to hold onto the transducer so it can't move away from them while they install the probe. That's actually the exact opposite of what we should be doing. If you recall, the probe is screwing directly into that center plate. If we hold onto the transducer, it's much too easy to exert excess force along the indentation direction. So instead, we recommend taking a mouse pad or some sort of sticky thing, placing the transducer on it. Take that tip tool, come up, and as you're installing, don't hold on to the transducer. Let it move away from you as you're installing. The second tip is to go backwards first. So that makes sure that the threads of the probe and the threads of the transducer are aligned. In really quiet labs, you can actually hear the click as those threads align, but mostly people feel it. It's really obvious. So backwards, feel the click, and then you move forwards. Keep in mind that you're holding onto the back of this probe tool. And the reason for that is that the probe tool has a spring in it. So you're holding onto the back, you're twisting it in. Typically, I do a 2-finger or 2-hand motion to continue it moving. You're going to reach the end where the spring engages. Now, the spring, it works like a poor man's torque wrench, meaning it's not going to stop you from over-tightening necessarily, but it does allow us to all tighten to the same torque, meaning finger tight to me means something different than finger tight to you. But if I tell you to go, into the spring engages and then an extra quarter to a half turn, it's going to be about the same amount of force against that spring for everyone. So that's what we recommend. You then pick up the transducer, you come over and you slide it onto the piezo scanner. And then this is also a spring-loaded tool, this transducer, the blue-handled transducer tool you can see in this picture. And there is a little set screw you can see here. And we tighten that the same way. You tighten the screw until the spring engages and then go an extra quarter turn to make sure it's securely tightened. I also recommend that you always slide the transducer fully onto the piezo scanner, meaning there is a sidewall here. So this side is open. This side has a stop. So slide left to right, and then hold your finger against the transducer as you tighten it so it doesn't jump away. Doing so will make some of the calibrations easier. It's not the end of the world if you don't, but it should be as far on that piezo scanner as possible. Any questions on hardware right now?
We're good. Yeah, I do remember the procedure of cleaning that, but it'll be of cleaning and replacing it, I guess. But it'll be good if you can do a live demo. I mean, we can try it.
Okay, I can share the documents and you can see if there's any confusion, and we can do a live demo on the next meeting should we need to.
Okay, sounds good.
Okay, the system then ships with two sample standards. You have a fuse quart standard, which is used for the tip area function as we discussed, and then you have an aluminum standard. The fuse quarts you can clean the same way you clean the probe, meaning you can use either methanol or acetone followed by isopropanol. Unfortunately, cleaning the aluminum is very hard. Any cleaning, it seems, scratches the surface of the aluminum pretty significantly. The best thing I found is to use compressed air or dried nitrogen and shoot it across the sample to remove any debris. So I think with that, whenever you're ready, you can go ahead and share the instruments screen and we can train on what that looks like. Okay, so our first question is the hardware installed properly? So is it correct that the tip is a Berkovich probe is installed in the transducer and that the transducer is installed on the instrument?
Yes.
Okay, what's on the stage? What do we have for samples right now?
The two sample we mentioned are the fuse course and then the aluminum.
Okay. All right, so question one is done. Is the hardware installed correctly? For our purposes, yes. If it was you, you would also have your sample hopefully on the stage. And then we go ahead and we start up the software. And this is the screen that will greet us, and we'll go through all these screens one by one throughout the course of the training. But here we have the sample navigation screen. The second question is, have I done my indentation access calibration for the day? So this needs to be done at least once a day. I typically do it every time I open the software, throughout testing sometimes if there's something strange going on. So what that entails is after the software starts up, it takes a while to start. We've already had this started, but we know it's live when in the upper left-hand corner, there, can I take control?
Yes.
I might not, oh, there it is. I'm not going to click, but I would like to point.
Sure.
There I am. Okay, so this is my mouse. So up in this upper left-hand corner, we have the active status of the transducer. Once this starts updating, we know that the software is live. It also, when it starts up, it's always grayed out. So you'll see it become ungrayed out as it starts up. So here's our sample force. So this is what the tip is feeling in the air. So, okay, software is live, we're good to go. The first thing you should do after starting the software is go to system calibration. I'm going to let you drive. I'm just going to point. Good. And we have several, so these are accordion menus and we have several subscreens. This is the system general screen. This one here. And it's the default that it opens to. And the first thing we need to check is, do we have the correct transducer calibration file loaded? So if you recall, I was talking about how we calibrate the transducers to have a displacement scale factor and load scale factor. And those are done at the factory using a laser and like an interferometer and a mirror on the end of the transducer's probe, which allows us to calibrate. Each transducer is slightly unique, so these numbers vary a little bit. So we want to make sure that we don't have like the default file loaded by accident or that someone didn't load something else. So in the upper left here, we can see Hydrotron transducer calibrations, and then it has a serial number. And I actually haven't seen your transducer, but based on my knowledge, that looks like the correct serial number for your system. Is that correct?
I think so.
So here you have your load scale factor and displacement scale factor and a few other settings that we will go over in the course of training. The transducer electronics version we don't really talk about because it's version 2, and that's always going to be true. These might change slightly depending, but we'll talk about how to change them and when you need to change them. Similarly, so for the scratch axes, we will talk about this in depth when we get to scratch specific testing because I want to focus on indentation right now, but it should be noted that we also use a transducer laterally. So we also need that same load scale factor and displacement scale factor for the lateral transducer as well. So these are the constants. These are set at the factory. And when the transducer ships to you, you actually have a physical piece of paper that will have those numbers on it. So if there's any doubt, you can always pull that paper out. If you don't have the paper, you can email me, ask me for my records. I will get them to you. But these look like the correct numbers for this transducer. Sounds like you're checking. Good.
Yeah. I'm checking where is that paper.
Specifically, we're looking at the load scale factor of 1.12 and the displacement scale factor of 20.8108.
Is that an inspection report?
No, it's actually usually in the transducer box itself.
Oh, transducer box.
Mm-hmm.
Yes.
Good.
I have the indentation axis and the lateral axis. Yes, I have this document. 1.12, 28108, and point the electro or the machine compliance, and then the bias offset is not on this paper. The paper has electrostatic force constant, and then the plate spacing, and then the maximum force. Okay, it's there.
Yep. So these are true. These are always the numbers you're going to use. This 1.12 and this 20.8108. Those are calibrated at the factory. The machine compliance is dependent upon the system and will change from system to system, and even where it's installed can change it slightly. So that is a user updated or a service engineer updated field. That's why it's not in the sheet. And then the bias offset. So what that is, if you remember during that training document, I said, oh, this says top or bottom, but I know it's always the bottom plate. That's a physical thing. We can only get wires to the bottom plate. So the only way to control the transducer is to apply a voltage to the bottom plate, which means that we can only pull down. The problem with that is that that means if you go to 0 volts, you might not lift fully off the sample surface. So what we do is we bias the center plate forward. So right now we're biased at 1000 nanometers forward, so a full 1 micron. And that way, during a test, when we go to 0 volts, it will lift completely up and off the sample surface. It gives us the ability to have a lift, which is also important for re-zeroing, which we will see together as we do indentation.
Okay.
Here, this electrostatic force and plate spacing, the ones on the sheet are the ones that were just recorded at the time of testing at the factory. They're going to change slightly day to day. So this is part of this is the calibration that we need to perform, is that we need to update these values every day to account for changing environmental factors. So what we're going to do for this calibration is we actuate that center plate into the air. Now, you know and I know that we should feel zero force during that actuation.
Yes.
So the system takes, it does the actuation, it measures the force it's feeling, and then it takes the spring constant and says, well, I know how much voltage I put into those springs, and it switches the equation around and solves for the updating electrostatic force and plate spacing day to day. What this allows is that way when you indent into your sample, we know how much of that force went into moving the springs, not how much of that force went into your sample. So you get a real true force to voltage relationship between the force into your sample without the force into the springs intruding into that. So in order to perform this calibration, we have to go ahead and click, I'm going to let you drive again. You have to go ahead and click that calibrate tab. Sorry, calibrate button. That's the better term. And it's going to take us yep, go ahead. And it's going to take us to the load function screen. What's important here is that you can see it says cal air indent, meaning a calibration air indent. I bring this up because there are other ways to do other air indents, but they don't calibrate to it. Here we are entering a specific calibration regime that we need to do daily to account for changing environmental factors. So go ahead and click cal air indent, and we're just going to actuate out and back. And we get 3 live graphs here. We get load versus displacement, load versus time, and displacement versus time. I'm always looking at displacement versus time. Is the transducer moving? Because if it's not, that's your sign to call Laura. That means something's wrong, that we need to talk. So here we can see it actuated out to about 3925 nanometers, 3.9 microns, which is the majority of its range, which is what I expect it to cover. We then get this result. It's going to ask us, I can't see it. Does it say, do you want to save somewhere?
No.
Interesting. What version of software are we running? 31? Okay. In any case, you get this ESF versus displacement graph. And now the only thing people ever remember is that your RMSE should be less than 5 times 10 to the negative 5, as a rule of thumb. There's a little bit of wiggle room there, but that's our rule of thumb. Now, it's a good rule of thumb, and we should remember that. But the rest of the picture is just as important. My first question is, did it actuate? So in the background where the actual graph is, we can see it goes from -2 to 3927. And here in this graph, we're fitting from 0.8 to 3.5. So we're fitting to the most linear part of that actuation. Here we have the red line, which is the actual travel of the transducer, and then the blue is the fit. We should be looking at this, making sure the blue fit is linear, that it looks normal, that everything looks great on this graph. And then we should also be looking at the red. Now, I see some low frequency vibrations getting through, which is pretty standard for the TS77. What I'm looking for here is if there's a weird spike in noise, or if it's really noisy the entire way, or if there's a weird discontinuity or curvature. Those are all red flags that, oh, maybe my calibration file isn't loaded, maybe something else is going on. I should email Laura or the global tech support team.
Yeah. Laura, so 2 things. One thing is because there's a car just drive past. We're near a window, so maybe that's the vibration caused that. And also just realized that Dr. Nico remind me that there is a little window, since I have like a double screen, so it pop on the other screen. I just noticed that it did ask me whether I want to keep the file.
Good. Okay, thank you. So now that we have reviewed it, we can say yes, right? Because we know that it's less than 5 times 10. The RMSE is less than 5 times 10 to the negative 5. It actuated, it's linear. The noise is within the expected values. So we can go ahead and click yes. And you can see actually in the background, it also updated that graph. So it applied that new ESF and plate spacing. So you can go ahead and close the pop-up. Is this what it has looked like historically, this air indent?
Yeah.
Okay, that is what I would expect for this instrument, especially near a window. Are you guys on the ground floor? Is there a basement under you?
Our funny thing, our campus is kind of like on a slope thing. So on one side we're on the ground floor, but there are 2 floors below us.
Oh, interesting. I've never installed a system in that kind of. I know exactly what you mean. Huh. Do you think it's like Okay, so there is open air beneath the instrument somewhere.
Well, behind it is kind of like a hall.
Okay.
I mean, normally it's just like people walk around there, but once a while when the maintenance people are moving around, you might hear like a tractor sound or something like that. But
Okay. Yeah, I mean, there's nothing wrong with this air indent. I was just being curious. It has about a 1 micronewton spread. And sometimes on quieter systems, what we see is like a smiley face because we can actually see the actuation out and the actuation back. And there's some small hysteresis. Here, the noise is high enough that it covers that up, that it averages it out so we can't see that differentiation. But that's no problem.
okay.
So, yeah, this looks great for the system. So, okay, we have 5 questions. We're down 2 of them. Unfortunately for you, they're the easiest ones. Is the hardware installed? The answer is yes. The second question is, did I do my indentation axis calibration? The reason it's in this order, to be clear, is that the system cannot keep itself safe if it's not sensing force. There is an emergency stop that is installed in the probe, but if it's not actuating, if it's not sensing force, it can't work, right? So, okay. It's a sanity check of that too. So we did our indentation axis calibration, which meant that we also checked the cal file. So those 2 things are done. The third question is, are all of my samples defined? Or at minimum, is my tallest sample defined? So our system is what I call an optics-led system. What that means is that everything we do is from a focal point, right? We say, go do an indent here or go put an array of indents here, but those stage coordinates are tied to the optical location. So the system, it will have automated moves in order to go from the optics over a sample to the tip in contact with the sample. It needs to move up to some, height and then move over. So that height is predicated on the tallest sample's focal height. If you don't define the tallest sample, you run the risk of crashing the transducer against a tall sample and breaking the piezo scanner, and at worst, the transducer. That's how I see them get damaged most often. Now, I did just say that there is an emergency stop. That's only on the actual probe itself. The transducer housing doesn't have any sensors. So it's only if we apply force to the probe that the emergency stop will occur. So, third question, are our samples defined? And the answer is no. So we are in what we call the default workspace. The default workspace saves your sample zones and your methods so that you can see in this upper right-hand corner. So let's go ahead and let's make a new workspace for us today for this training.
So when or after we accept that, that's how on this page we need to do. We don't need to execute the fit.
Nope, because we're not testing a material, right? So the execute fit button, what that does is it does that power law fit to the unloading curve of an indent, and then you get your reduced modulus and hardness. Here, that's not what we're doing, right? We're doing a calibration. We're just indenting into air. So there is no fit to be had. So there's a drop-down menu where we can make a new workspace. It's asking you if you want to save the current workspace, and you can click. I don't know if you've changed anything, so I don't know. So it's asking you what you want to save. So you said, yes, I want to save the workspace, and it's asking you what do you want to save the current workspace as. So this is for the current workspace. It's asking you what do you want to save the current workspace as. So this is still your default. Now it's asking you, do you want to make a new workspace? So you go ahead and click yes. And then, oh man, they changed the order. Now it's asking you, what do you want to name this new workspace? So don't you want to name this one Bruker Training?
Yeah.
So let's go ahead and click. And click OK. Okay, so we're going to start by defining our sample zones. There are 3 different ways to define samples. On the system, we're going to start with the most basic one, which is we need to focus on the sample surface. So we've been brought back to the sample navigation screen, which is great. On this screen, we can see we have an optical view that right now is dark because I can see our X, Y, and Z are in the home position, meaning we're not over anything, we're just homed. We can turn on and off the scale bar for this optical view, and we can also turn the reticule on and off. Down here, we have intensity for the light, so we can turn that up if we need to. The problem with this is that there is some auto balancing that happens as well. This will be more obvious on an actual sample. Generally, I find somewhere between 0 and 5 is sufficient. Sorry, this is hard to control remotely. Oops. Up here, we have our stage navigation. So we have X and Y, then we have Z here. You can see that there are crossbars, and then there are these squares, concentric squares going out. The squares are speed. So the further out you are, the faster the stages will move. The closer you are, the slower. In order to move the stages, you have to click and hold. So you click and hold, and then it moves. Once you get down to more fine movements, we highly recommend doing slower, longer moves than doing really quick, short moves. The reason is that your stages are not encoded. So if you do a bunch of short, quick moves, you might run the risk of like the steps being off. The system doesn't like it. The software might crash. So longer, slower moves rather than many short, fast moves. You also have your Z, which works the same way. So this brings the Z stage up. This brings the Z stage down. And the speed is dependent on where you click here. Down here, you have your safeties, where you turn them off to save the system. I'm going to move things. I will keep the system safe. It won't let you move the stages if you're below the Z fly height in X and Y. So I'll have you go ahead. Let's start with the aluminum sample because that's going to be the easier one. Let's go ahead and get the optics over the aluminum, and then I'm going to have you define the sample. One thing that's kind of annoying about round samples is that our system is, can you see this? Yes, okay, it will show up. Our system is XY, which means that it can be hard to move around a circle like this. If I can give you a little bit of advice that I learned from a different service engineer is to define in straight lines. So we're going to focus on this sample, and we're going to find the apex. Oh, this is not working. Of that, we're going to find the apex of that circle and put our first point here. And then you can drive straight south to find the bottom edge. Then drive at 45 to find this. Straight across to find the other one. And that's your first square. And then you can find your new, you got to move it like a weird 30-degree angle. And then you can define a second square here with these 4 points. And that will make defining a circle much easier. So let's go ahead and move an X and Y and Z and get over the aluminum sample.
Okay.
Good. So as he's moving down below, we can see that there's some stuff moving here too. This is supposed to be an example of what the stage looks like. The circular pink portion is where the optics are over the stage. And then the green diamond is the probe. There we go. I was going to say, are you moving? And the answer was going to be no. And the reason why was because the safety needed to be disabled. Now we're moving down in Z.
Yeah.
Is everything okay? I don't see the Z stage moving anymore. Yep, we're getting pretty close. I would expect it to be about that distance.
Okay. I'm gonna put another camera here so you can see it.
Thank you. There it is. So we went straight through the focal point. Don't go down. Stop.
I think I'm getting too close.
Stop. We did see the focus point. We have to go back up.
There's no voice from you, Laura, for some reason. Oh, 1 second. I'm sorry.
No, it's okay. My microphone's been going in and out, so I was disappointed, but I'm glad you can hear me. Yep, so we went through the focal point, so we have to go back up to see the focus again.
Oh.
Yep, that looks like the aluminum standard.
Yep.
Okay, so let's go ahead and let's click New Sample. Okay, and let's rename the sample. I usually just call it AL for aluminum. Sorry, there is a button that says Rename Sample right below New Sample. Yep, there we go.
Just aluminum.
Yep. Okay. And then go ahead and, like I said, find the top part, the very apex part, and we're going to put a point there to start defining the sample.
Put a what? I'm sorry?
So you're going to move an X and Y, and I want you to find the very top of the aluminum sample. Like
okay.
the northmost point is how I'll put that.
Okay, let's see. Oops. Too fast. It's hard to tell whether this is the top or the side.
Well, so that curvature, right? It's a circle, so we're seeing the curve, if you think about where the circle is. So go to the left, or sorry, let's call it west slightly.
This one?
I wouldn't go that fast, but yes. Yep, let's go in negative X. You see how we're climbing up the side of the circle? So we'll find the highest point. Okay, I think that's good. We can start to see it coming back down slightly. So go ahead and click Add Position here. So that's under quick, all of that information, Add Point, excuse me. So that defines the first point of our sample zone. We need at least, 3 points to define a plane, obviously. So go ahead and drive straight down to find the south point of the aluminum sample. And the aluminum samples are typically tilted, so what we're seeing is the focus change as we travel.
Oops.
Good. I think slightly to the east. Positive X direction. Good. I think right about here, maybe even back a little bit. And then go ahead and, refocus to make sure that we're getting the best focal point. And then you can go ahead and click add point when you're ready. Okay, now we have a line. I suggest driving at a 45-degree angle until you find the easternmost point of the sample.
Right here, this way?
Yep. Mm-hmm.
Ooh. Why have to
You do
define
a,
this large?
I'm sorry?
I'm sorry. I thought like earlier, I think in the training we just did a quick like boundary. We didn't like define all the points.
Yep. So quick boundary is the second way to define a sample, which we will cover. And that works really well if you have, if you're loading a sample and you just need a little bit of it that you need to test quickly. You can do that. Certainly, that's not a problem. Here we are defining the whole sample for a couple different reasons. One, you're going to use the sample zone often. And two, it actually helps us during the calibration process. Three, you should be trained on how to define an entire sample. The purpose of sample zones is that is what the system will let you test in, right? It doesn't matter if you have a sample that's this big, if you only want to test this bit of it, you can just define that bit. It doesn't particularly matter to me as long as it's defined in some way. It's just that if you do that, you're not going to be allowed to test over here on that sample because the system doesn't know that the sample is there. As far as it's concerned, it's only as big as you've defined it.
Mm-hmm. Ooh, sorry.
It is also good practice for learning how to use the stages and move around.
Yeah. This is a good egg.
I think so, yeah. And then I would go straight across. I'm sorry. I meant straight west, so that you go straight across the sample to find that other point, to make a diamond.
In here?
Yep. Now go straight west, negative X, just negative X. There you go. Because now you'll find the westmost point of the sample. Yeah, and then you can move south a little bit to find that curvature. Yeah, I think now we're on the other side. So you can go ahead and focus. Yeah.
Okay.
Okay, now we can go ahead and add this point. So now you got one square, now you have to make the other one. So I would travel at 45 degrees up and then move out to find the next point. We were trying to find that point. Let's see, that's the northwest point on the sample.
Mm-hmm. So now I can just drive. Now I'm kind of like here. I can just go down to get this point.
I'm not sure I'm following. Well, so if we think about the sample, right? Do I still have control? Where's my mouse? No, maybe. My mouse disappeared. I'm going to stop control and take control again. There it is. So the point is that you have a round sample, and I wanted to find as much of that round sample as I can. So right now we're missing these pieces. So I needed to define a point here, 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 and here to give me all of that sample.
Okay. So I think I need to drive, like, since now we're kind of like on the edge here, I need to drive up to get this one.
So if you drive it so you're pointing here, if you click there, you're going to move the optics this way, away from the sample.
So right now I am on the wrong sample, like it's a wrong sample. Draw thing.
Sorry, what are you looking for?
I said for this square now is this the top and this is the bottom? This is a left and this is a right?
Mm-hmm.
So I'm on the if the circle I'm on the left. So now I just go straight up. I should reach out like this point.
Well, go ahead. Go ahead and try it and just see what happens. See if we can figure this out. Best way to learn is to try, right?
Yeah. So you see the curve is going like sort of go up. I assume is a point somewhere like here.
Well, we want the point to be somewhere like here. Right, because we want to define this as a curvature. We want to define this as a circle finally. So we're doing that by making two squares. So this is the first point on this second square that we'll define here. So I need you to find the northwest apex.
Northwest. Is oh no. Oh, is this the dots that's showing like where the
Yep, that's where your optics are. Yeah.
Oh, so that can
that's
be
where
my
you're focused
guide.
on. Exactly. Yep.
Ah, okay.
Good. There you go. You got it.
Yep.
That's good. That's where I want you to be. So now you go ahead and add this point.
So I need to focus every single time, correct?
You should. Normally samples are much flatter than this. This is not a great example of a nano indentation sample, but that's because we're not going to get data off the sample, which we'll explain as we go through training. But yes, you should refocus if you need to. But on your samples, I wouldn't expect this much tilt. Okay, now you can drive straight across again to get to the next one.
Oh, I think you've reached the end.
Oh yeah, I did notice that we had the biggest stage travel. You can't move any further?
No.
Okay, is the AFM puck inside of a sample zone? Meaning when you look on the
it's here.
Let me see. Sorry, I'm going back and forth. Okay. Can we pause from training for me to try a couple calibrations quickly for service? These are service performed calibrations that you don't need to do, but I would like to do them quickly if that's okay with you.
Of course.
Okay.
You want
I'm gonna go. I'm sorry? Yeah, pause the video if that's okay.
Sure.
Just to stop any confusion. So what I'm gonna do